So we've got a great speaker coming up to really talk about that, really kind of deep down insides of Node.js. So I want to welcome Colin to come on up and give us a little insight around Libuv and the unicorn Velociraptor.
All right, thank you for coming to my talk, everybody. I hope you enjoyed the last talk, because it's all downhill from there. So this talk is about Libuv, and we're going to try to answer the question of what is a unicorn Velociraptor. So the way I answer any question is to ask Google. And this is, I don't know if the results have changed since the last time I Googled it, but this is what Google gives you back. I think this row is probably my favorite, collectively, with the Chicago Bears football player riding a dinosaur, a cat riding a unicorn. But we're here to talk about this Libuv, which is a platform abstraction library used by Node.js. So Libuv was primarily developed for Node.js. It's not exclusively used by Node. So we have several other consumers. CMake is a big one, Julia, which is I think, scientific programming language, NeoVim, some other ones. Libuv is nice because it's written in very basic C, so it's pretty portable to a lot of different platforms, and it gives Node access to features that don't come from the JavaScript language itself, like the file system, DNS lookups, different child processes, things like that. So the first thing I want to talk about is the platforms where Libuv is supported. I want to start off by introducing Saul, the little cartoon head down here. Saul is actually another one of the maintainers of Libuv, and he has a lot of good one-liners that I didn't want to take credit for and not attribute to him. So Saul may pop up from time to time at the bottom of the slides with useful pointers. In this case, it's we write the if-def so you don't have to. So if you've ever written C code, you've seen probably this pound if-def thing. It kind of tells the compiler to include or exclude a piece of code. And if you look through the Node.js code base, we don't actually have a ton of platform-specific code. A lot of that has been pushed down into Libuv. And so if you look through the Libuv source code, there is actually a lot of if-defs. So we have an entire separate implementation for Windows from everything else. And then we have Mac OS versus all the different Linuxes and basically all the different platforms under the sun. But we specify 3 levels of tiered support. So the first one is going to be Linux, Mac OS, Windows, and FreeBSD at the top. These are going to be the platforms that we run the CI on every single commit. If the tests fail and breaks one of those platforms, then the patch needs to either be reworked or left out completely. Breaking those platforms is not really an option for us. Then at tier 2, we have SmartOS, Go Joyent, AIX from IBM, Muscle Linux, and ZOS also from IBM. The interesting thing about this tier is I think we actually need to rework it, because these are the ones that are supposed to be officially supported but not necessarily tested in the CI. SmartOS, AIX, and ZOS are all tested in the CI, so some might argue that they're tier 1. And then we have tier 3, which is going to be Android, IBM, SunOS, and basically every other platform in the world. These are the ones that are going to be community maintained. So if you and a couple of your friends get together and build an operating system, you want Libuv to support it, you can try submitting a pull request. If it's not too invasive, it might get accepted. But we're not going to test it in the CI, and you're kind of on your own to make sure you fix it if it breaks. If it breaks and no one fixes it, it'll get removed. Next, I wanted to talk about some of the features that Libuv provides. So probably the most famous one is Node's event loop. Talk about that a little bit more in a second. Next are TCP and UDP sockets. So if you use Node's net or dgram modules, they're coming from Libuv. DNS resolution, Libuv provides one of the two ways to do, and go back. One of the two ways to do DNS lookups. Does that look right? Oh, I guess so. All right. So Libuv provides one of the two ways to do DNS lookups. I'll also come back to that in a little bit. File system operations and file watching are things that basically the entire FS module is going to come from Libuv. And then some other things, child processes, Node's child process module, threads, other synchronization primitives, and then we have a high resolution clock. So if you are trying to do some type of benchmarking and date.now is just not accurate enough for you, you can use process.hrtime and it'll give you a higher resolution clock. So this isn't an exhaustive list of features, but it covers most of them. So this is what Libuv looks like at a very high level. So I like to break this diagram up into two rows. The top row, which is going to have more of the user-facing APIs, and then the bottom half, which is going to be more of the guts and the implementation details. So like I was saying on the previous slide, sockets, TTYs, pipes, things like that. Those are all going to be asynchronous I/O operations that come down into either ePOL, KQ, event ports, or IOCP. That's going to be depending on what operating system you're running on. So ePOL is going to be used on Linux. BSDs and Mac OS are going to do KQ. Event ports are going to be for SmartOS and Solaris systems. And then IOCP is used on Windows. Then in the bottom right, we have the Libuv thread pool. That lets us execute work off of Node's main thread because by default, JavaScript is single-threaded. And I'll talk about this a little bit more coming up, but basically the only things that are going to run in the thread pool are going to be file I/O, DNS operations, and user code that you can write C code to submit jobs to the thread pool. One of the most important things, like an important concept to understand when it comes to Libuv is the concept of handles. These are going to be abstractions for usually long-lived resources. So if you have a socket or a child process, things of that nature. We also have a second type of handle that is basically invoked at certain points through the event loop, and I'll show you that on a diagram in a couple slides. So if you were interested in kind of instrumenting the event loop, you could use one of those. And then handles are important because they're what keep your event loop alive. So if you were to write a basic Node.js server, the reason whenever you run the server that it doesn't exit is because the server has a handle associated with it, and as long as that handle is active and something called refed or referenced by the event loop, it's going to keep your process from exiting unless you do so by force. You can also unref an event loop, so if you have that same server and you call unref on the handle, then even though you have a server running, your process will exit. Another concept that kind of goes along with handles are requests. I like to think of handles as objects and then requests as either methods or functions. I say either methods or functions because sometimes they're associated with handles, other times they're their own standalone thing. And so examples of requests are going to be socket connections, streaming operations, DNS operations, and then things that you pass user-defined work past to the thread pool. And like handles, these will also keep your process from exiting. So if you were to write a simple Node.js file and all you included in it was a DNS lookup, the reason that Node will wait until the DNS lookup completes to exit is because that request is keeping the event loop open. And then Node actually has two unofficial APIs for inspecting the handles and requests. If you do process._getActiveHandles and _getActiveRequests, you can kind of get a glimpse inside the event loop. Coming back to the thread pool, this is what gives the illusion of Node doing multiple things at once. Like I'm sure you all know, JavaScript is single-threaded, so blocking the event loop is generally frowned upon. But you can actually take pieces of code and offload them into the thread pool so they'll run on a separate thread. And this was really important before we had worker threads in JavaScript. But the condition there is that you're passing off C code. It's not going to be your JavaScript code. And so the size of the thread pool can actually be configured. Unless you need to mess with it, I would recommend not. But the UV_thread pool size environment variable can be set at startup, and it'll configure the size of the thread pool. By default, it is 4 threads. One common misconception is that everything runs inside of the thread pool. That is completely fake news. So the only things that actually run in the thread pool are file IO, get address info, get name info, and then any custom requests that the user might provide. So this is what the event loop looks like at a high level. If you actually were to go into libuv and look at the C code, it's not organized all that differently from this. So we keep a concept of the event loop time. We do that, we perform that once at the beginning of each iteration, and we cache it because it's fairly expensive to keep computing that. So after we have the event loop time, we check, is the loop alive? So basically, are there any handles or any requests still referenced and active? If there's not, then the process ends. If there are, then we drop down into basically another tick through the event loop. So the first thing we do is run do timers. So for example, in Node.js, if you do set timeout or set interval, that's going to have a libuv timer associated with it at some layer in the timer logic. Once those expire, they're going to be executed. Next, we would call pending callback. So if you started some operation in the past and it's now, like a file operation, it's now complete, we're going to run the callback for that. Next, we run something called idle handles. So they're actually very poorly named because they kind of imply that they're run whenever there's nothing going on with the event loop, but actually they're executed every time, every tick through the event loop. These are a good way to basically, like I said before, do some type of instrumentation with the event loop if you need to. Next, we run prepare handles. So these are handles that are executed just before we begin polling for I/O. Then we actually step down and do the I/O polling. So if you recall a few slides ago when I talked about IOCP, event ports, KQ, and whatnot, we're going to poll for I/O at this point. After that's done, we're going to run check handles. So check handles are kind of like an inverse operation to prepare handles. So one executes before polling, one executes after. And then finally, if there are any handles being closed, this is where we're going to run the close callbacks. I also wanted to point out, so this is kind of the extent that I'm going to talk about the event loop. If you want to know more about the event loop, check out Bert Belder's talk from Node Interactive 2016. It's a really good one. Also, you'll notice there's no promises in this. Promises are kind of a special snowflake. They're implemented with a microtask queue in V8 and have nothing to do with libuv. So now that we've kind of talked about the structure of libuv, I wanted to talk about how libuv integrates with Node.js. So in this diagram, everything in yellow is going to be your JavaScript code. The stuff in purple is going to be very nasty C++ code. Nothing against C++, but this particular C++ code is very nasty. Down here at the bottom, we have the operating system that we don't really care about. And then here we have all of the different, or not all of, but most of the dependencies that are actually compiled into the Node.js binary. I organized them like this because the talk is about libuv and then kind of everything else. But in reality, it would probably be V8 and then everything else. So obviously V8 is the JavaScript engine from Google that lets you actually execute your JavaScript. OpenSSL is where Node gets all of its cryptography primitives from. C-Aries is another way that Node does DNS lookups. So it's interesting, we have two different ways. There's the one that's used by libuv, which is going to be the same as your system resolver. So for example, if you were to do ping and then provide a host name, libuv is going to look up the address the same way that ping would. C-Aries is going to do something a little bit different. It makes a network request to look up what your DNS information is. And the interesting thing about libuv's DNS system is that For a while, up until recently, you could actually kind of shoot yourself in the foot a bit if you used too many DNS operations, because by default we only have four threads in the thread pool, which need to be shared between DNS operations and file system I/O. Those used to conflict, so we would get bugs on the issue tracker, people issuing a bunch of DNS requests, and then all of a sudden their file system operations stopped responding. So that's no longer an issue. That's actually been fixed so that no type of thread pool operation can consume the entire thread pool. Just a little fun history there. And then Saul is back to introduce the onion architecture, where the more layers you peel back, the more you will cry. So if you've done any work with Node's net module, you've probably come across net.socket before. It's pretty easy to use streaming JavaScript object, but inside it has something called a handle, which is where we drop down into that nasty C++ code, which is going to be implemented as something called a TCP wrap. If you were to dig through that code, you'd find that the TCP wrap also has its own handle, which points to something called a UV TCPT, which is going to be TCP inside of libuv. And then finally, libuv wraps whatever the actual underlying operating system socket is. So the next thing I wanted to talk about a little bit is testing with libuv. We currently have over 300 unit tests. They are written in C. They are a pain to add new ones. It's just a little bit tedious. And we've actually run into problems in the past. Sorry, I got a little bit distracted. A pop-up from Rich just showed up on my screen over here. But yeah, so we actually we would cut a new version of libuv, and then we would go to update it inside of Node, and then we would find that when we ran the Node test suite, things were breaking. And the system worked fine because we would catch it in the Node CI. We wouldn't necessarily go ahead and, we would go and fix libuv and then create another version, and is kind of an ugly process. But there are actually people out in the world who, as soon as a new version of libuv is released, they go and they build Node themselves. And so for these people, even though we didn't strictly break Node, we kind of provided a less than ideal user experience for them. And so this is just an example of, with version 119 and 119.1, how this happened. We broke some people, we got things ironed out, and we moved on. But we kept thinking, like, there has to be a better way. So what if we went and used Node's test suite to run libuv before we cut a release to make sure that everything is hunky-dory? And the build group was nice enough to provide a CI job for us that does exactly that. So you can run Node's master branch compiled with a libuv branch. They kind of get mashed together, run Node's test suite, and see what happens. And this is nice because Node has over 2,300 tests, probably more than that since the last time I updated this slide. And they're written in JavaScript, so they're fun to write. A lot easier than writing C code. And ever since this has happened, we haven't had that issue that I talked about where we would have to cut multiple releases. That's not to say that no regressions have occurred, but not that specific problem, which is nice. So next, I kind of wanted to walk you through a call from JavaScript code down into the C++ binding layer, down into libuv and back. And to do that, I'm going to illustrate with a copy file operation. So this was added in, I think, Node 8.5. We have fs copy file and copy file sync. And more recently, we have a promises-based version. So if you weren't aware of that, you can go out and play with those. It's kind of cut off down here at the bottom, but basically these are the synchronous, the callback-based one, and the promises-based one. And then that's your user code. If you actually then look inside Node's JavaScript standard library, I picked the promises-based code just because it's a little cleaner and fits more nicely on a slide. There are similar functions inside of core that do the same thing for callbacks and synchronously. But basically what we're going to do, so what we're doing here is we're going to validate the source and the destination of the copy operation. This flags statement is going to be any type of flags that the user passes in, like, you know, if you try to do a copy operation and the file already exists, whether you should overwrite it or not. The little pipe and then 0 on the end is a V8 trick that forces the number to be coerced into an integer. So you know JavaScript has a number data type. It has no concept of integers, but the underlying JavaScript engine actually does have that concept. So that's just a little trick there. And then finally, we call binding.copyFile. So binding is what's going to actually drop us down into the C++ code. And this is what the different calls to binding.copyFile look like, depending on whether you're doing callbacks, promises, or synchronous. And you'll notice that the first 3 parameters are the same in all the cases. So your source, your destination, and your flags. Those are the inputs coming from the user code. The last 2, or 1 in the case of the bottom 2 lines, arguments are what let the binding code kind of differentiate between the different operations. So the K use promises, for example, is a symbol that in the C++ code, it can look and see if it gets a symbol, then it knows it's doing promises work. And so this is what the C++ code looks like. I was sitting in the back, so I know you can't read that. The screen's not great. And it's also the most code that I'm going to show, so please bear with me. But basically, we're going to do some input validation. I don't know if you can read it. These say check. The check is basically going to do some type checking. If the checks fail, the process is going to abort. We're okay with that because, for one, all the proper type checking is supposed to be done in the JavaScript layer already. And 2, if users are using the binding layer directly, then you are kind of on your own. You're not supposed to do that. So after we do some input validations, we call something called getRecWrap, and that is going to return a value that is going to be either null if you're doing a synchronous operation, or not null if you're doing promises or callbacks. And then appropriately, we drop down into this either async dest call or sync call. I'm not going to go through what all the different arguments are because there's a lot and most of them don't matter. But if you can read the screen, you'll see that it says copy file, the word uv_fs copy file, and then the source, destination, and flags. And so that's going to translate into calling uv_fs copy file inside of libuv. So at this point, we have left Node core and dropped down into libuv. We're out of the C++ into the C code. The very first thing we do is call init copy file. So the init is a macro that's going to expand, and basically for this rec object, it's going to tell the rec object that it's a copy file operation. The reason we have to do that is all the FS, like file system operations, share common code. So whenever we submit something off to the thread pool, it has to know what exactly it's supposed to do with it. After we do the init macro, we check all the different flags. So this is just making sure that the user didn't pass in flags that libuv doesn't know how to handle. If they did, we return an error. Finally, we're going to copy more arguments onto the request object. So this path2 is actually going to copy these 2 paths onto the request, and then this statement is just going to assign the flags on the request. And then we call post, and post is another macro that's either going to submit work into the thread pool, or if it's synchronous, it's just going to execute and return the result. And so that's what this looks like. This is the macro expanded out. Basically, we check if the callback is null or not. If the callback is not null, then we're going to register the current request with the event loop. That is basically just going to increment a counter so that libuv knows that there's something it should be watching out for. Next, we call uv_work_submit. So that's going to submit your request into the thread pool. uv_fs work is basically a giant switch statement. It has all the, so for example, when we did the init copy file, that's going to be the condition of the switch statement. So that's where it's going to know what it needs to do. And then UVFSDone is the C equivalent of a callback function in JavaScript. And then after we submit it, we just return. In the synchronous case, we actually call UVFSWork directly. So it'll actually perform the copy synchronously. And then this rec.result will have the result of our operation, and we just return that directly. And so after all this happens, then we'll step back out of the C code, back out of the C++ code, back out of the Node's JavaScript standard library, and up into back to the user code. So if you wanted to know what the copy file operation actually looks like, this is what it looks like on Mac OS. So Mac actually provides a system call for us to use, so we just need to coerce some flags between what the user passes in and what, like to libuv and what the Mac OS system call actually expects. There's actually, this is for Mac, there's a different implementation for Linux and all the other Unices that's gonna depend on first trying to do send file, and if send file doesn't exist, then it's gonna fall back to copying bytes manually. It's pretty nasty and definitely would not fit on a slide, so you can feel free to go look that one up yourself. And then this is what the Windows implementation looks like. If you remember, I said we have a separate implementation for Windows and every other operating system. In this case, Windows provides copy file W, which lets us do the copying, so we just need to do some more input validation and then let Windows do its thing. And like I said, after this, then we just kind of bubble back up into the different layers. And then the last thing I wanted to talk about tonight was libuv 2.0. So libuv 1 was cut back in 2014, so it's now over 4 years old. It still works fine. It's been mostly API and ABI stable the entire time, save for the occasional accidental break, which we then go back and try to fix. But there are some things there are some new features that in order for us to add them, we would need to either break API or ABI. And so at this point, we need to kind of move on with life and leave the 1X branch behind. The problem is we have a very small team of maintainers compared to the army of people who work on Node.js. And Node 10 is not end of life until April of 2021. Since libuv 1 shipped with Node 10, we have to at least provide some type of support up until that point. But we definitely need to get libuv 2 out the door, preferably before Node 12. There's not really that many breaking changes, but we can't ship them in a non-breaking release. So normal Semver major housekeeping things, taking a chance to clean up old code, clean up things we don't need anymore. We've added some functions to work with CPU affinity. There's actually multiple of these functions. Some of them can be backported without breaking ABI, others can't. If you've ever used Node's os.userinfo function, it basically looks up a password file entry for the current user. We added a field to that function that would return the human name of the user instead of just the machine username, but it breaks the ABI, so we have to push that off. And then some other functions for working with timestamps related to it. So if you can, some operating systems allow you to set the birth time of a file, others don't. But we haven't been able to add those in a non-breaking way yet. But like I said, in general, there's not too much going on there. And that is all I have for tonight.
Okay.
So obviously Node uses uBlink, but are there any other Node projects that use the library?
Yeah, so CMake, so libuv can build with CMake, and CMake depends on libuv, so it's a nice circle of life.
Yeah.
Julia Lang, NeoVim, a couple years ago Rust did, but Rust has outgrown libuv. Other smaller projects, but yeah, there are definitely others.
And what's your licensing?
Open source. I don't know the exact, if it's MIT or not, but it's free for anyone to use.
And for
Node uses V8 and libuv. So what happens when you run code in V8 and it has to do asynchronous jobs? It talks to libuv or?
So, well, V8 doesn't, actually V8 does use libuv in some places inside of Node. Not obviously the V8 that ships in Chrome has no concept of it. But yeah, there's C code, there's C++ code in libuv or in V8 that does call libuv stuff inside of Node. Or were you talking about at JavaScript in V8? So JavaScript crosses from basically what I traced through. It calls that process.binding, and drops down into C code. In general, you want to avoid doing that as much as possible. It's actually expensive to cross the JavaScript and C++ boundary.
My question was a bit similar, like the integration of the run loop of libuv with V8. When does libuv starts calling the main function of the JavaScript, or when does it run the microtask of V8 and that kind of stuff? I wasn't quite clear.
So in Node, there's like I think it's W main and for Windows, and then just main for all the other operating systems. And you can like jump through a couple functions, and then you'll get to a place where they initialize the event loop, and then it basically goes into a loop that continues until the process is ready to exit.
Okay. So for the V8 microtasks, are you calling into V8 from the libuv every run loop to run the microtasks, or how does?
So libuv has no concept of the microtask queue. That's called from C++ code in Node, or it might be V8. Honestly, I'm not really sure on that point, but it's definitely not libuv.
What makes Android tier 3? Is that amount of usage, or it's difficult to support with your CI?
I think it's more about the CI, because there are actually a lot of people who show up wanting Android support. I would personally like to see it in the CI. That's pretty much what it comes down to. libuv uses Node CI to run all of its tests, so if it's not supported by Node, it really isn't supported by us.
Same answer for Node. Same answer for Node. Same reason Node would like to support Android,
yeah.
but for the same reason doesn't.
Mm-hmm. All right, well, thank you.
Sorry about the pop-up of comment. I'm really sorry.
It just kept popping up.
No, I said you told me I got 4 minutes to queue up. So.
All right, everyone. That is all we have for the talks, but the night is not over. We have my favorite part of the evening, what we basically call 15 seconds of fame. This is a chance for all of you to come up if you are looking for a job, if you are someone that is hiring at a company, or you want to share a really cool project that you have brought into the world and you think others might enjoy. This is your opportunity to come on up and promote yourself, promote your job, flash a resume in front of everybody. So